Hello everyone. Today we are going to cover chapter 5.5 equilibrium in 3 dimensions. Today we have 2 learning goals. First thing is I want you to know how to identify support reactions in 3-dimensional object. And also I want you to know how to draw free body diagram for the 3-dimensional problem. Apply equilibrium equation. So now we are talking about the 3-dimensional object. Last class we learned about the support reactions in 2-dimensional spaces. Do you remember the pin joint? Pin joint usually has 2 support reactions, which is x-axis direction and y-axis directions. That's 2-dimensional spaces. In 3-dimensional spaces, pin joint has 3 support reactions, right? For the x-axis direction, y-axis direction, and z-axis directions. So let's look at every single cases one by one. Here we have a cord. We call this is the cable. Cable, in this case, we have only one unknown. Okay, this is the support reaction. How about the smooth surface contact point? We have one support reaction. Typically, we set the orientations like this is the z-axis, x-axis, and y-axis. This is the orientation. Typically, we can set in the 3-dimensional spaces. In this case, only z-directional support reactions. We have only one unknown in this case. How about the roller? Roller has one support reactions, one unknown. This is interesting, ball and socket. If you look at the image, ball and socket here we have a small ball and socket is here. How many unknowns here? Ball and socket. We have restriction for the x-axis direction, y-axis direction, and z-axis directions. So there are 3 unknowns. How about the rotations? In this case, there is no restrictions for the x-axis rotation, y-axis rotation, and z-axis rotations. So only translational movements are restricted in these cases. But how about the single journal bearing cases? Single journal bearing is we can move this object for the let's say this is the horizontal movement. Okay, there is no restrictions for the horizontal movement, but we cannot move this way because this is designed that way. Also, we cannot rotate the object for this axis. We cannot rotate. So there is one support reaction and one support reaction about the moment. Okay. Also, we cannot move this to the vertically. Also, there is restrictions about the rotational movement. So total is 4 unknowns. We have 1, 2, 3, 4 unknowns in this case. How about this one? Number 6. It seems like we can move this one horizontally, but we cannot rotate this one because it's a square, right? So in this case, we have 5 unknowns. This one is added. Likewise, single thrust bearing is we cannot move, so there is a restriction for the translation, but the rotation is fine. So there are 5 unknowns. Single smooth pin pin has here, we have three support reaction for the translational movement. How about rotations? Rotation wise, for the x-axis rotation, it's fine, there is no restriction, but the y directional rotation and the z directional rotation, there is restrictions. So we have totally 5 unknowns for the smooth pin joint case. How about the hinges? Hinges, well, there is no horizontal movement as well as the vertical movement. Also, there is a restriction about the rotations, so those are all support reactions. But in this case, for the y-axis, rotation is fine. So there is no restriction for the rotational movement for the y-axis. In this case, the total unknown are 5 unknowns. Fixed support. This is the most restrictive way to hold the object. Here we have a totally 6 unknowns. We cannot translate for the vertical and horizontal in any directions, so there are support reactions. How about the rotation? We cannot rotate for any axis. So total is, we don't know 3 translational forces. We don't know the 3 rotational moment. This is the real example about the ball and socket joint. So you can see that this one is ball and socket is there. So this one has how many unknown forces are there? We have 3 unknown forces for the translational movement. There is restrictions, but rotation wise there is no restrictions. Single journal bearing. Single journal bearing is we cannot move this way and this way, but we can move this way, so there is no support reaction here. Also we have a rotation things, so single journal bearing has 4 unknowns. Single truss bearing is we cannot move the translation. Also this rotation is restricted, but this axis rotation is allowable, so there is no restrictions. Smooth pin, how many unknowns? 2 unknowns. Oh, never mind. 5 unknowns. 3 translational restriction and 2 rotational restrictions. When you apply the equation of equilibrium in 3 dimensions, these 2 conditions must be satisfied. If you sum up all the forces, the total of all the forces should be equal to 0, which is a translational movement. The rotation should be also equal to 0. So here in 3 dimensions we can express all the forces in Cartesian vector format. So all the forces should be equal to 0. So there is no x-axis movement, y-axis movement, and the z-directional movement. Any point at point O should be equal to 0. That is a moment, right? So we can set the orientation x-axis, y-axis, z-axis. Every external forces can create the moment any point O, but since we are dealing with the stable object, the rotational tendency should be equal to 0 for the x-axis, y-axis, and the z-axis. You can see the sigma here. So when you add up all the moments that is associated with the x-axis, y-axis, z-axis, each moment should be equal to 0. So if we have 6 unknowns, then it's solvable because we have 6 equilibrium equation. Now let's apply this equilibrium of equations in problem. Okay, but before we go to the main problems here, I want you to understand there is some concept you have to understand. This is very important in statics. When you design something, when you design some machines or object, you have to think about the constraint and the statistical determinacy. Okay, what does it mean? Constraint is when you design some object. This constraint is you have to hold the object properly with the constraint. So, for example, this case here we have a roller support at point A and B, and here there is external forces. If you look at the direction of the forces, it's a little diagonal directions. Okay, there is some angle here, so that means even though we have a two support at point A and B, this roller can only support the z directional movement, which is vertical directional movement. But in this case, the external forces was directing from a little angle from the horizontals. So in this case, this beam can be moved in these directions. How about this case? We have a cord here, cable. As I said, cable has one support direction. This is a vertical translation directions. But here, the external forces are acting from the left-hand side. So in this case, this object can be shifted a little bit because of these external forces. So we call this is a constraint. Okay. So you have to design the constraint to hold the object in stable positions. We don't want the machine move with the external forces. We have to secure that this bridges or this building is safe enough and it's not move. Okay, because we constrained the object by properly designing the support reactions. And sometimes this is another case. If you design the object with too many support, that's not necessary, or the support is not enough to hold the object in 3D space. That's also a problem. We call that is statistical determinacy. Statistically indeterminate, that is the issues. So for example, this is the redundant constraint. We have a support at C, but we don't need this one. Why we need this one? It creates another issues. Okay, the B, we don't know the support reaction at point B, so this is still unknown, and this one we don't know. So support reaction at point C, this is unknown, this is unknown, and this is the fixed object. We have two support reactions as well as there is a couple moment. So there are too many unknowns. So don't make the problems. This is how can I say? This is the increase the level of difficulty. So statistically indeterminate situation. There are too many unknown supports. Then we cannot solve the problem because of too many unknowns. All right. Let's solve this problem together. The homogeneous plate has a mass of 100 kilogram. Okay, there is a 100 kilogram mass subject to the force moment along each edges. Okay, it is supported in the horizontal plane by a roller A. We have a roller A. Okay, how many unknown we have at point A? We have only one unknown, so roller has support only z directional movement. X-axis, y-axis, There is no restriction for the roller. How about the ball and the socket joint at B? B has all the restrictions. There are restrictions, but there is no rotational restrictions. How about the chord at C? We have only one unknown, that is the support reaction by the chord. Okay, so we have one unknown, three unknown, and another one unknown. So total will be 5. And remember, this object has a weight that is 100 kilogram times 9.8 meter per second square. This is 180 Newton. And this 180 Newton external force is acting directly in the middle of the plate. So that is, this one is 1.5 meter, and this one should be 1 meter because it's half. It's a center. So let's draw free body diagram for this quiz. Okay. Okay. This is roller, and this one is ball and the socket, and this one is supported by the cord. And then we have a one couple moment here, which is 200. Okay, let's set the orientations. In this case, let me set the upward direction should be Z, and this direction, let's say this is X and this is Y. Okay, let's set the orientation this way, and let me draw some unknown forces here. Since point A is supported by the roller, there should be one support reaction. Let's call this is AZ. Ball and the socket at point B has a 3 unknowns, 3 support reaction. That is BZ and BY. Remember, the direction is my assumptions. Okay, the direction is not that important in this case. After that, when we solve the problems, then you will realize what is the right direction based on the sign. See, we have one support reaction, which is a CZ. Okay. Now we have to apply equilibrium equation. Okay. For the x-axis, which force is associated x-axis? Only bx, right? Only bx. This one is equal to 0. Okay, it's a piece of cake. We directly find that, oh, bx, this one is equal to 0. How about the y directional forces? Is there any forces associated with y directions? Yes, by. By? Any other? No, so this is 0. How about the z directional moment? Okay, we have another many forces associated with the z directional movement. So this is cz and minus 300 and minus Newton. How about the x-axis rotation? Now it's a tricky one, but let's find the rotations about the x-axis rotations. Here we have x-axis. How to find the rotations? Well, if I were you, I will choose point B to find the x-axis directional rotations. Why? Why we choose B? Because B has a lot of unknown variables are associated. So if we choose the point B, then we don't need to worry about these three unknown forces about the rotational moment, because we already choose the point B, and every single force, the perpendicular direction to the point B is equal to 0. So this one does not create a moment at point B. So let's choose the point B to calculate all the moment associated with the x-axis movement. So you can see that the x-axis direction is this way. So we want to identify which forces are associated with the x-axis directional movement. We can say that, oh, this one create this 300 Newton create the never mind, it's a clockwise rotation. So clockwise rotation, which is minus, and this one also create the clockwise rotation. By the way, this CZ create a counterclockwise, which is positive. So let's write here minus 300 Newton times the perpendicular distance is 1.5 meter minus t times, oops, times 5. How about CD? Okay, let's move on to the y directional rotations. Where is the y direction? Okay, this is y axis. So let's choose point B. Still, we want to simplify the problem. So this is y axis. Which force create the y axis rotations? So first of all, I can see that AG create the clockwise rotations. Clockwise rotation. So, which is a positive. AZ times 2 meter. And this 300 Newton still create the rotations about the y-axis. But in this case, this is a counterclockwise rotation, so it's minus. Remember, when we set the direction of orientation, this is a positive x-axis, this is a positive y, and upward is positive z-axis. And what else? This 980 Newton create the, this one is create counterclockwise rotation about the y-axis, so this one is minus. Times, this is 1 meter. Okay, I think that's it. This is for the. How about the z directional moment? Let's choose a point B for the z directional movement. This is z directions, but in this case there are no forces associated with the z direction, so z direction is 0. But wait a minute, I think I missed this one. This one is copper moment, and then this one is directing what is this one is rotating this way. So what is this? This one is x-axis rotation. This is copper moment, and the direction is minus direction. So I missed this one, sorry guys. This one I should add a 200 Newton. Should be equal to. So what I wanted to say here is from this equation we can directly find AZ, which is 790 Newton. And we can also find the CG directly from this equation. So CZ is equal to 270 Newton. Since we know that AZ and the CZ, we can identify what's the BG from the third equation. BZ is equal to let's see. Oh, wait a minute. I think I made a mistake. This one is 117 Newton. So you can find the answers here. Note that once you calculate the BZ, you may see that the sign should be the negative sign here. So that means our assumption for the z directional support direction was the upper way, but based on our calculation here, this one should be downward directions, not the upward directions. Okay, so support direction at point B for the z directional movement, it should be the downward direction. So support direction is pointing downward. Okay.